So I'm Sriram Bhyravarapu. I'm a postdoc here at IMSC. The topic of the talk will be on planar coloring. So how many of you know what's a planar graph? Okay, so there are a few people who know and most of you are not aware of this. Okay, that's fine. Let's go slow. So in this talk, we will see what's a planar graph and what is a planar coloring and the history behind this planar coloring, and towards the end of the talk we will see one coloring algorithm on the planar graph. So that's the agenda. So it all started in 1852 when Francis Goutrey took out the map of England and started coloring the countries in such a way that no two regions which share a common boundary are given the same color. So this problem is called the map coloring problem. Let's look at it with some examples. So consider the map of India. So this is a coloring, and you see that Maharashtra and Madhya Pradesh, they share a neighborhood. There is a boundary which is common between these two states, and hence they are colored differently. Maharashtra and Chhattisgarh, they share a common boundary and they are given distinct colors. Similarly, Maharashtra, Telangana, Maharashtra, Karnataka, right? So now the problem is to assign colors to the regions such that no two regions which share the common boundary get the same color. That's the problem. So if this is given to us, can you come up with a trivial upper bound on the number of colors required? How many colors do you think are sufficient to color this graph such that which satisfies our requirement? When I say my requirement, it's the thing that no two regions which share the common boundary are given the same color. Number of states, right? Basically the number of regions, right? That's the trivial upper bound. So now what do you think of, suppose there are 28 states and let's say you have 1000 regions. Now what's the upper bound? 1000. So when you say 1 lakh regions, 1 lakh. So can you come up with a good, can you think of some good upper bound on the coloring number? So it's, all of you are right that number of regions is a trivial upper bound, but can you come up with some better upper bound? Oh, those of you who have seen it, please.
Maximum adjacent regions.
Maximum adjacent regions. So you say Chhattisgarh, so number of regions adjacent to it?
No, whichever is the nice.
Yeah, let's say that, but then I could have something like this, right? So I could have a region like this and I could have lot of such things, right? So, and these regions may be unbounded, 1 lakh regions are there here. So in that case, again, you may need 1 lakh, right? That's what you wanted to say. But any answers? Okay. So while coloring this map of the countries of England, Goutrey, he noticed that at least 4 colors were required to satisfy our requirement. And he also conjectured that 4 colors are sufficient to color this graph. So now let's see some facts. So this map coloring problem can be converted to a graph coloring problem. So how do we convert it? So for every region, you create a vertex. So these regions have a corresponding vertex and you need to add the edges between the vertices. You add edges between two vertices if they share a common boundary. So this is the resultant dual graph of the map. Now the question is, you need to color the vertices of this graph in such a way that no two adjacent vertices are assigned the same color. So this is the graph that you obtained. Now the problem boils down to assigning colors to the vertices of this graph such that no two adjacent vertices are assigned the same color. So it is also known that the graph that you obtain from this graph is planar. Now what is planar graph? A graph is planar if it can be represented by a drawing on the plane such that no two edges cross each other. Correct? So this is a K4, a click on 4 vertices. Is it a planar graph? So this is a planar graph, right? But there are 2 edges crossing each other. So in its current state, it is not a good representation, but so let's see, this edge is drawn like this. Now there is a drawing for this graph where all the adjacencies are maintained, the neighborhoods are maintained, the degrees are maintained, and the graph is intact. It's a planar graph. So what about this graph? There are no two edges crossing each other. In the current state, it itself is a planar graph. The same holds for this. So what about these graphs, K5 and K33? So these are not planar, right? So maybe it's a good exercise for you to look to see why these graphs are not planar graphs. Okay. Now let's go back. So we saw that the map coloring problem can be converted to the graph coloring problem, and the graph that we obtained from this map is also planar. Now the question now is to ask the following. The conjecture says every planar graph is 4 colorable. Now it boils down to coloring the planar graph. It is believed that the planar graph is 4 colorable. Now let's look at the history. In 1854, Guttray published this as an open question in a literary magazine. Again in 1860, Morgan posed the same question in the same magazine. In 1879, Cayley raised this problem at the meeting of London Mathematical Society. So in the next year, Kempe claimed to settle this conjecture. For this, he was elected as the Fellow of the Royal Society and later the President of London Mathematical Society. So in the next year, Tate also claimed to have another proof. Unfortunately, the proof that was suggested or claimed by Kempe is incorrect. After 10 years, Hayward showed that there is some fault with the Kempe's argument. But using this Kempe's argument, he was able to modify this algorithm and come up with a 5 color algorithm. Instead of 4, he was able to show that every planar graph is 5 colorable. So that is what we will be seeing towards the end of the talk. So there is one more proof by Tate. In 1891, Peterson showed that Tate's proof was also incorrect. So at this point of time, there is no algorithm that is known for detecting if a planar graph is 4 colorable or not. So over the next 100 years, efforts have been made to reduce the number from 5 to 4. So in 1904, Wernicke introduced this technique called discharging technique in order to solve this 4 color theorem. So let's look at this discharging technique on a high level. So this is the technique that is used to prove certain things in structural graph theory. So the basic outline of this talk is you need to have a list of subgraphs. And the thing is that every graph that satisfies a particular property should have a subgraph from this list. You need to come up with a specified list of subgraphs, and you want that every graph that satisfies some property should contain a subgraph from this list. So that's the basic outline. And the presence of this subgraph is often used to prove the results. So this proof contains 2 steps. The initial step is giving the charges to the vertices of the graph. You give charges to the vertices of the graph such that the sum of charges could be positive, negative, such that the sum of the charges across over all the vertices of the graph is a positive number. So that's the starting phase. Now comes the interesting phase, which is called the discharging phase. So in the discharging phase, you have certain discharging rules. These are the important things. So set of discharging rules is an important thing. So what happens is you need to frame some rules such that if the graph satisfies that property, you need to distribute the charge on a vertex to its neighbors. Whenever a particular property is satisfied, you say vertex V satisfies some property. The charge on this vertex V is being distributed to all its neighbors. So notice that in this process, the overall sum of charges on all these vertices remains equal to the sum that you started with. The sum of charges that you started with will now be equal after every discharging step. So that's the invariant. So the rules are designed in such a way that after the completion of discharging phase, every vertex with a positive charge lies in one of the desired subgraphs. So, on a high level, this is the thing. So there is this theorem called the theorem in 1904, which is proved by this discharging technique. So, which states if a planar graph has minimum degree 5, then it either contains an edge where both the endpoints have degree 5, or one of the endpoint has degree 5, the other endpoint has degree 6. So, now to solve this, they have solved this using discharging technique. For that, first you need to come up with some specified list of subgraphs, and then specify some discharging rules, some way to distribute the charges on the vertices to the other things, and say that at the end, after application of this discharging rules, every vertex with a positive charge is in one of the desired subgraphs. Okay. So, let us come back to the history again. So, then there is this proof by computer. In 1960s and 1970s, he developed methods for using computers to search for proof. So, he was the first one to use this discharging technique to solve the 4-color theorem. So, with the help of Ken Dore, a computer test was developed. Unfortunately, he couldn't get hold of a supercomputer that he could work with to solve this. But using his ideas, in 1976, Apple and Haken, they announced a computer aided proof using the ideas of Haywood, the 5-color theorem, and Kempe's theorem. So, the idea is the following. So, if the 4-color conjecture was false, then there would be at least one map with the smallest number of regions, smallest possible number of regions that requires 5 colors. Right? If the 4-coloring conjecture was false, then there should exist at least one map with the smallest number of regions, and that requires 5 colors. So, now the idea is to show that such a minimal graph cannot exist. When I say it is a minimal graph, when I remove something from this map, it becomes 4-colorable. In that sense, it is minimal. All of you are with me? Okay. Okay, so the idea is to show that such a minimal graph cannot exist. So, towards this, they introduce this notion called configuration. What is a configuration? A configuration is a connected subgraph of G with the degree of each vertex in G specified. So, let us say I have a graph G, I say there is a vertex with degree 1, there is a vertex with degree 2, there is a vertex with degree 3, this is a configuration. So, these are some configurations, this is configuration 1, configuration 2, configuration 3. So, this is a connected subgraph, one vertex is a connected subgraph, and I also mention the degree of this vertex, this is 1, 2 and 3, right. So, these are the configurations. So, now they define something called reducible configurations. So, a configuration C is called reducible configuration. Let us say a configuration C is available. Now, if I remove this configuration from the graph G, and if this is 4-colorable, then G is 4-colorable. If there is a configuration that satisfies this thing, which means that I remove this configuration from the graph, and if it is 4-colorable, and if the original graph is also 4-colorable, then I call this configuration as a reducible configuration.
What do you mean by remove the configuration from the graph?
So, there is a, let us say, what is the configuration? The configuration is, let us say there is a region of degree 1, the number of neighbors is only 1. So, let us say I remove him. If the remaining is 4-colorable, then you should be able to say, if the original is also 4-colorable, then this configuration is called a reducible configuration. The configuration is coming up with a graph, a subgraph, let me call a subgraph H, and the degrees associated with each of the vertices. Okay, so now they define something called unavoidable set of configurations. So, so these are the configurations where every graph should have a subgraph that contains in this set. So this is a set of configurations like C1, C2 and so on. Take any graph, it should contain a subgraph that contains in my set. So that is my unavoidable set of configurations. Like it hits. There is a configuration which is available as a subgraph in the graph. So now the objective for them is to compute an unavoidable set of reducible configurations. So they want to combine both of them, unavoidability and reducibility, and then they say that if I am going to compute an avoidable set of reducible configurations, I am done. So recall that when we say it's a reducible configuration, when a configuration C is reducible, it means that if G minus C is 4 colorable, then G is 4 colorable. Let's look at a contrapositive. So this says that if G is not 4 colorable, then G minus C is also not 4 colorable, correct? Okay. So now let's say we are trying to build up a counter example for this 4 color conjecture. So what do we want? So we want to say that we want to build up such a minimal graph such that there exists a map with the smallest number of regions that requires 5 colors. This is what we are trying to go towards, right? So let's say if there is a graph which is a counter example for us, and it cannot be colored using 4 colors. Yes, it is not colored using 4 colors. Then since this is true, this is definitely true because of the reducible configurations. So now you are saying that okay, the original graph is not 4 colorable, and also after I remove the configuration again it is not 4 colorable. But this violates something. What does it violate? So this is the smallest number of regions that requires 5 colors, right? So which means that if I remove something, it is 4 colorable. But what he's saying that even after remove the configuration, it is not 4 colorable. So which means that the counter example that you are looking at is not minimal. There is something which is further minimal, correct? So now they show that there is no minimal counter example. Okay, this is how they say that okay, there is no minimal counter example. Okay, so initially there were 1834 reducible configurations, and then they brought it down to 1482 configurations. So and then checking one by them, if it is a reducible configuration, it took over 1000 hours. So and there were some back and forths on this algorithm, and in 1997 Robertson and others, they came up with a simpler proof using the same ideas, and the number of reducible configurations is 633. So in 2005 Gonter proved the theorem with the general purpose theorem proving statement, and this solves the conjecture. Okay, this is the high level picture of what is happening. So if you want to look at this unavoidable set of configurations and how they are built, there is a 400-page book where they have written all these configurations. You have to manually check whether this is how it is unavoidable and why is it a reducible configuration and things like that. Okay, so now let's look at this 5 color theorem. So we all know, how many of you know this Euler's theorem? Okay, fine. Most of you don't know, that's fine. So if G is a connected planar graph, so maybe I'll skip this part, so I don't need this. So let me go to this. So let G be a connected planar graph, and if the number of vertices in the graph is at least 3, and m is the number of edges, then the number of edges is at most 3 times n minus 6. Please take it for granted this theorem is true for those of you who have not seen this. Okay, so towards proving the main theorem, let's prove this auxiliary one. If G is planar, then G contains a vertex with degree at most 5. How many of you have seen this proof? Okay. Okay. So if G is planar, then, okay, please don't look at this. If G is, oh, now your attention is now diverted to this actually, right? Okay. So if G is planar, then G contains a vertex of degree at most 5. So how do we go about it? Any ideas? Proof by contradiction, okay. So suppose that every vertex has degree at least 6, right? And we saw in the previous slide that if G is given to be planar, then M is at most 3n minus 6. So this we saw in the previous slide, please take it for granted, okay. This is well established, well known. Okay, so now how do we rewrite M? So is there any relation between the number of edges and the summation of degrees of the graph? So there is a handshaking lemma, right? So what do you get from there? Oh, maybe I missed that side. So you get the summation of the degrees of V is equal to twice the number of edges, right? And then we say that M is at most 3n minus 6, right? So from this, what do we have? This is at most 6n minus 12, correct? So now we have assumed something has a contradiction. Every vertex in the graph has degree at least 6. Now can you come up with a lower bound for this quantity? This should be at least 6n, right? So you are saying that the degree of every vertex is at least 6 and there are n vertices. So this quantity should be at least 6n. So now if you look at this inequality, so this is a positive number and it is sandwiched between 6n and 6n minus 12, which cannot happen, right? So whatever we have assumed initially is incorrect, and hence that there exists a vertex in a planar graph of degree at most 5, okay? Okay, so now let's come to the main thing. So in 1890, he came up with this proof. He said that every planar graph is 5 colorable. So the proof that we gave is induction on the number of vertices. How many of you know what is induction? Okay, okay. So it is induction on the number of vertices. So since we are looking at 5 colors, right, the base case would be to say that, okay, if n is at most 5, then G is 5 colorable. Why is this true? Can you come up with the coloring if n is at most, let's say n is 5, then why is this true? G can be colored using 5 colors? Trivial. Why is that? How is it trivial? Can you come up with the coloring? What's the coloring? So the claim is that every planar graph is 5 colorable, right? So you need to give me the coloring of these vertices, right? So and I tell you that the number of vertices is 5, and I'm also telling you that the number of this graph is 5 colorable. Can you give me a coloring? Yeah, you give a distinct color to each of the 5 vertices, right? So no two even whatever is the configuration or adjacencies between them, it doesn't matter to us. Okay, so now there is this induction hypothesis which says that, okay, on I minus 1 vertices, any graph on I minus 1 vertices is 5 colorable, right? Any planar graph on I minus 1 vertices is 5 colorable. Now let's say we are given with a graph, planar graph on I vertices. How do we go about it? Let's say we are given with a planar graph. So what did we see in the last slide? There exists a vertex with degree at most 5, right? So in this graph G also there should exist a vertex of degree at most 5. Let's play around with that vertex. Okay, let's say that V is the vertex which has degree at most 5, and let's say we remove it from the graph. Okay, so G minus V, does it contain? So you say that if V is removed from the graph, what is the number of vertices in this graph? I minus 1, right? But what does the induction hypothesis tell you? So this is 5 colorable, right? It says that it is 5 colorable. Okay, so G minus V is 5 colorable. Now you put back V. What color do you give to the vertex V? Right, this is G minus V and it is 5 colorable. Now there is this vertex V that you brought it back, and this could have arbitrary adjacencies. But what is that thing that you know for sure? The degree of this vertex is at most 5. That's the only thing that we know, right? Okay. So what happens if the degree of V is 1? Can you come up with a 5 coloring? Yes? What color do you want to give? Different from its neighbor, right? Okay. So if the degree of V is 2, different from the 2 colors, right? If the degree of V is 3, the same process. If the degree of V is 4, so in the worst case it could have C1, C2, C3, C4, you give C5. Yes, it is 5 colorable, right? Right? Even if you bring back V, it is 5 colorable, correct? So now the problem is, what happens if its degree is 5, correct? So you are in a good case, good situation, when the degree of V is at most 4, correct? So now what happens if the degree of V is equal to 5? So are there any good cases even though we have the degree to be 5? Yeah, suppose that 2 of the neighbors are using the same color, correct? So then there is one color which is missing in its neighborhood. You can assign that color to him and you are done, correct? Okay. So now let's come to the difficult case. If all the neighbors are using 4 colors, then you can use the 5th color to him and you are done. Now let's come to the difficult case. Suppose that every vertex is using different color as depicted in the picture, and how do we go about it now? So recall that this is a planar graph. This is a planar drawing. Okay. So I'll first look at does there exist a path between V2 and V4. Okay. Not just a path, but an alternating path in terms of the colors. What do I mean by that? I start with V2, check if there is an red, green path from V2 to V4, starting at V2, ending at V4. Okay. If there exists such a thing, or there is no such thing, correct? These are the 2 cases that are remaining to us. Let's say that there is a red-green alternating path. What can you say about V5 and V3? Can you say something about V5 and V3? Do you think there can be an alternating path between V5 and V3? So recall that this is a planar graph and there is a red-green alternating path between V2 and V4. Now the question is, take this intermediate internal vertex V5. Now the question is, does there exist a violet yellow alternating path between V5 and V3? There cannot be, right? Why? Sorry? So if it has to have an alternating path, it has to cross this boundary, right? But you are saying that all the vertices here are either red or green. So if it has to cross, it should have a neighbor either red or green. So there is no violet yellow alternating path between V5 and V3. Okay. So now what we can do? We know that there is no alternating path between V5 and V3. What can we do? So look at the color here, yellow. Let me swap the colors. Let me swap the colors violet and yellow in this region. Okay, just in this region, let me swap the colors violet and yellow. It does not affect anything, right? Right? Because they are not connected to outside world. All its am I audible? All its yeah, it does not affect the outside world. So what will you do? You just swap the colors violet and yellow in this region. Now what happens as a result of it? V5 gets yellow. Now you see that there are only 4 colors being used in its neighborhood, correct? Now you see there are only 4 colors, right? Blue, red, yellow and green. Now you have space for the 5th color. Assign the color violet to the vertex V. Okay. So this case is done. Now let's go to the other case. So the other case is, there is no red green alternating path. Maybe I'll give you a minute to think on what should be the next step. What happens if there is no red green alternating path? Okay.
You can swap the color
Of?
red and green within a component.
Sure. Okay. Okay, what she suggests is to start with V2 and then change the color of V2 to green. Now as a result there can be some conflicts, right? Because initially it was colored red, he could have some green neighbors. As a result there are some conflicts. Whenever there is a conflict, change the color to red, right? Change this color to red. So if there is a neighbor with a different color other than red and green, it doesn't matter to us in any way, correct? It still satisfies the proper coloring. The only things that we are not happy with are these conflicts. So if there is a conflict, V2 is assigned the color green. Now there are some conflicts. Now what do? Change the color of these 2 vertices. Keep on doing this. Now there can be some conflicts again, right? So now these two people are happy. Now there can be further conflicts. Now change W4, give it green. Keep on doing this, right? Can such a situation arise? W4, V4?
But arise it goes to the first case.
Yeah. So this kind of a situation cannot happen because it's a V2, V4 alternating path. This cannot happen, right? Okay, so now what do you have? The red is freed for you. You can assign the color red to him, correct? Now it's a 5 coloring. Okay, this sums up the proof. Let's analyze the algorithm. Okay, how much time does this step take? The base case. Suppose I tell you that the number of vertices in the graph is n and the number of colors is k. Can you give me some trivial algorithm to check if there exists a k coloring of this graph? Okay, let me repeat the question. I would request you to please be silent. So let's say you have a graph on n vertices and you are given with k colors. You can play around with k colors, you need to come up with some algorithm such that you color the vertices of the graph using k colors such that no two adjacent vertices get the same color. I mean, what's the
All possible combinations of colorings.
all possible combinations of colorings? Is it all possible combinations of colorings? So this is like you are enumerating all possible subsets of k, right? And choose k. So this does not give you anything about the coloring the entire graph. So you should slightly vary your thoughts. So you are on the right direction in some sense, but so can anyone suggest a brute force or greedy thing? Greedy. So he was suggesting something called of the order n power k. So which we all agreed that it's not correct. So can you come up with something else? Brute force. Do you think there can be an algorithm of running in time k power n? Can there be an algorithm running in time k power n? What does k?
Each vertices can be choose k colors.
Sure.
So k into k.
Okay. Okay. Thank you. So what he says is that you have n vertices. Each vertex has k choices. Either take the color 1, color 2, color 3, so on up to color k. So each vertex has k choices. So you have n vertices. K into k into k, n times is k power n. So that's what he's suggesting. So now, what do you think about the running time of this? So if the number of vertices is at most 5 and you are looking at 5 colors, is it a polynomial time algorithm? Is it a polynomial time step? Right, it's a polynomial time step, right? You just plug in the value k is equal to 5, n is equal to 5, there are constant number of things, and once you have a coloring, you can just check if two adjacent vertices are assigned the same color. Okay, so this step is fine. And now let's go to this step. So how do you check if the degree of v is at most 4? You can directly go to the graph and check, right? Let's just look at the neighbors. This is also fine. And okay, so now let's say now this is the thing. So now you have v2 and v4. Now you need to give me a red green alternating path between v2 and v4. How do you check? How do you decide? There are two possibilities. Either there is a red green alternating path or there is no path. How do you decide? How much time do you need to decide? So all we are doing is this procedure algorithmic, right? Or is it existential? That's what we are going to look at. So we are going to analyze each and every step and seeing if we can come up with some algorithm running in time n power o of 1, some polynomial time algorithm. Okay. So now how do you check? I give you two vertices v2 and v4. How do you check whether there exists a v2 v4 alternating path or not? So v2 v4 red green alternating path. How do we check? Okay. So how do you what do you start with?
From vertex 2, I traverse the first layer. If there is a green layer, green vertex, and then I follow that and continue.
Okay. Okay. So he's right. So probably what you can do is just delete all the vertices other than red and green. Just ignore them. All the things that are interesting to you are only the green and the red vertices, right? None of the other things are really helping you in any sense. Just keep track of the red and green colored vertices. Now, as he says, do the BFS and check if there is a component or if there exists a path from V2 to V4. That's all we need, right? If there exists a path from V2 to V4. If there exists a path from V2 to V4, then it means that there is an alternating path between V2 to V4. Correct? So how much time does it take? BFS, how much time does BFS take? M plus n? Okay, so it's polynomial time, right, again? Okay, nice. Okay, so even if there is no red green alternating path, what do? We started with some vertex V2, and then we looked at all the vertices here, and then if there is a conflict, we changed and kept on moving to the next phase, right? Correct? So how many steps can we do it in the worst case? How many steps can we go? We can only go to n steps, right, because there are only n vertices, right? We will definitely stop. So this is also a polynomial time algorithm, right? Polynomial time step. Okay, so overall all the steps are running in polynomial time, and hence this is a polynomial time algorithm. Okay. Okay, now let's come to the last slide. So is graph coloring polynomial time solvable on planar graphs? That's the question we want to address. So what we have seen till now is, given a planar graph, can you color it using 5 colors? The answer is yes. That is what we have seen. It does not mean that. What is graph coloring? Graph coloring asks us to come up with a minimum number of colors. Maybe I give you a planar graph and ask, can it be colored using 4 colors? Can it be colored using 3 colors? Okay, let me ask this question. Let's say I have a planar graph. Can it be colored using 100 colors? Some people from that side. I have a planar graph. Can it be colored using 100 colors? Yes? So we saw that every planar graph is 5 colorable. So if it is 5 colorable, is it 6 colorable? No. So when you want to ask if the planar graph is 6 colorable, yes, I can do it with 5 colors. I don't need a 6th color, right? So is the planar graph 100 colorable? Yes. So suppose if the number of regions is 1 lakh, how many colors do you need? At 5 is sufficient, definitely. You know of an algorithm, right? So now you understand, right? Even it does not depend on the number of regions. Okay. Okay. So the answer is no. So what's the question? The question is planar R colorability. Given a planar graph, and I also give you an integer R, the question is, does G have a proper coloring using R colors? So what are the values of R? R could be any integer from 1 to infinity, right? It could be any number. So what happens when R is at least 5? Okay, okay. What happens when R? Okay, let's go to 2. What happens when R is 2? I give you a planar graph and ask this question: is it 2 colorable? Who said yes? Is it polynomial time? Is there a polynomial time algorithm? Yes? Okay, what is it? Oh, you just told, okay. Now, how many of you have heard about bipartite graphs? Okay. So, what's the specialty of bipartite graphs? 2 colorable, right? So, graph is bipartite if and only if it's 2 colorable. We all agree to that? So, isn't it just sufficient to check if the input graph is just bipartite? Right? It's a planar graph, correct. But if we can check if it is bipartite, then we are done, right? It's 2 colorable. All of you agree to it? But how do you check if it's a bipartite?
Keep assigning colors using DFS.
Okay.
And if you are not able to color it, each time we color it, we check the adjacent vertices, and if they become same, I mean, if there's a collision, then we.
Okay. So can you think about any of the graph traversal algorithms where you can find out whether a given graph is bipartite or not? So instead of looking at this coloring thing, yeah, I agree to that, what you said, but Do you think BFS or DFS helps? I give you a bipartite graph. Can you make use of BFS or DFS in order to check if the given graph is a bipartite? How many of you know what is BFS and DFS? Okay, okay. So you know what is BFS, right? Okay. So can you think in terms of BFS? Okay, probably you can do that using BFS. So there is a, so BFS again takes polynomial time, order of n plus n m time, and hence it's polynomial time solvable. So given a planar graph, you are asking me to check if it is two colorable. I just run BFS on it, check if it's bipartite. If it is bipartite, yes, it's two colorable. Now let me ask this question, what happens to 4 and 5? Planar 4 colorability. I give you a graph and I give you a planar graph, I ask you whether it is 4 colorable. What will be your answer? Do you need to compute something? No, right? You know that something already exists. You don't need to do anything. Yes, there exists a 4 coloring to it. All you need to do is yes or no, right? So what about 5 coloring, 6 coloring, 7 coloring? All of them are definitely yes, right? Because you know 5 coloring is yes. Okay, so interestingly there is this 3 coloring thing which is not in polynomial time, which makes the life hard. So this problem is hard, NP hard, so it gets reduced from 3 colorability, and hence that's why we are not able to decide whether a planar graph is 3 colorable or not. I give you a graph and I ask you this question, is it 3 colorable? So this is an NP hard problem. Okay, so that's why we are not able to answer this question on this graph class. So for all the other values of R, we are happy, but only for this very particular case, there is this hardness. There is no algorithm, there is no polynomial time algorithm. Okay, so I will end the talk with these slides. So there are these characterizations for this planar graph, which says a finite graph is planar if and only if it does not contain some subgraph which is a subdivision of K5 or K33. A finite graph is planar if it does not contain K33 or K5 as a minor. And there is also an algorithm which can decide if a given graph is planar or not, and that algorithm is in linear time. It's a bit complicated one, but yeah. Okay, thank you so much. So this ends my talk.